Hello guys, welcome back to another video, and as promised we are looking at problem sets. Now in this video we're going to be looking at this particular problem, which is dealing with what? Velocity. But I'm going to be killing two birds with one stone. So in this particular problem we're going to be looking at the time of flight and the velocity. So let's get into it. Now the question reads, a projectile is launched from off a level ground with a velocity of 50 meters per second at an angle of 30 degrees with the ground surface. Then the question goes, find its velocity at ground impact, or find its velocity at the point of impact to the ground. That is basically what this means. So first and foremost, what we have to do is draw a diagram so that we understand what is happening here. So our projectile has been launched at an angle of 30 degrees to the ground surface. Now, let's say this is the ground surface. What we have here is this. 30 degrees, and the magnitude of the velocity being what? 50 meters per second. 50 meters per second. So this is what we have, and we were asked to find the velocity at ground impact. So this is the velocity during the launch. The velocity at ground impact is this. Let's call it VR. That is resulting velocity. So this is the velocity at ground impact, and this is the initial launch velocity. Now we could just say, what is the velocity at ground impact? Since these two are at the same level, the magnitude is the same. So this is 50 meters per second, and this angle, remember what I mentioned in the previous lectures, is equal to 30 degrees. So the velocity at ground impact is 50 meters per second at an angle of 30 degrees with the ground. We could say that, but in this case we want to go through the method of calculating. I want to show you how exactly we calculate this velocity without using the tricks I showed you in the previous lectures. So let's get into that. So the first thing we have to do is find the time of flight. Why am I saying this? I'm saying this because I'm going to be utilizing this equation. This equation of motion. I'm going to be utilizing this equation of motion in order to answer this question. So the first thing we have to do in this case is find the time of flight. How do we find the time of flight? Now, we could say the initial velocity in this case is 50 sine theta, the acceleration due to gravity. Now, let's assume the acceleration due to gravity is 9.81. I'm going to write it here, meters per second squared. Let's assume the acceleration due to gravity is 9.81. Now, given that the initial velocity, what is the initial velocity in this case? The initial velocity is, now my coordinate system is oriented in this way. So in this case, my initial velocity is what? It's positive. 50 sine 30 degrees. Let me rub this off. 50 sine 30 degrees is my initial velocity. And the acceleration due to gravity is what? Is 9.81. And the time, what is the time? Now, we could find the time of flight simply by doing this, by putting in the final velocity, but we do not have the final velocity. That is the final vertical component of the velocity. We do not have it. So bear in mind that this is the vertical component, the initial vertical component. The initial velocity is this, but the initial vertical component of the velocity is this. So in this case, in order to find the time of flight, what we're going to do is break this into parts. So that we have T1 over here. Like I mentioned in my previous videos, and t2 over here. If you do not understand what I'm doing here, go and watch my video on the time of flight. So what I'm going to do is I'm going to find this time, but since this parabola is basically symmetrical, the time of flight is going to be 2 times t1 or 2 times t2 if you will. So using this portion of the diagram, the final velocity at this point is 0. So we've got 0, that is the final vertical component of the velocity is 0. What is the initial? The initial is 50 what? 50 sine theta. See, 50 sine 30 degrees plus what? Okay, let me make this a bit smaller. So we've got 50 sine 30 degrees plus what? Minus 9.81. I always make my acceleration due to gravity negative. Hence this becomes positive. But if my acceleration due to gravity was positive, this would be negative. That is, I'll put a negative over here. So I've got minus 9.81 here. And what is the time? That's what we're looking for. So because this amounts to a negative, we can bring it over to this side and get a positive. So we've got something like this. 9.81 t is equal to 50 sine 30 degrees. So we've got 9.81 t is equal to 50 sine 30 degrees. And how do we find our t? Remember, we're looking for t1 in this case. Let's label it as t1 over there. So how do we find our t1? Our t1 is equal to 50 sine 30 degrees all over what? All over all over 9.81. So this over here becomes our t1. But we want the time of flight in this case. So we simply multiply this by 2. If we multiply this by 2, we get 2t1. But if we multiply this side by 2, this turns into 100. So we've got 100 sine 30 degrees all over 9.81. And this is equal to what? This is equal to what? The time of flight. So this is our time of flight. So what are we going to do next? We're going to utilize this equation again, and we're going to utilize this initial velocity again, this same acceleration due to gravity, but now instead of putting this 50 sine 30 over 9.81 as the time, which is equivalent to t1, we're now putting 100 sine 30 degrees all over 9.81, which is double this time. That is the time of flight. Doing so will give us the final vertical component of the velocity. But remember, we're not looking for the final vertical component of the velocity. We're looking for the velocity at ground impact. That is the final vertical component of the velocity plus the final horizontal component of the velocity. That was what we're looking for. But in this case, we want to calculate the final vertical component of the velocity, and then we'll calculate our horizontal component of the velocity, and we'll add the two so that we get the what? The velocity at ground impact. So let's do that. Now I'm going to write this over here. So this is 100 sine 30 degrees all over 9.81. So this over here is our time of flight. So I'm going to rub this portion now. Now we want to find the final vertical component of the velocity. That is this. We want to find this part. We can already calculate this. It's easy. That's 50 cos 30. But we want to find this component of the velocity. so that we add these two, 1, 2, and get this velocity at impact. So how do we calculate our final vertical component of velocity? So we've got v. The initial is still the same since we're using the time of flight in this case. So the initial is 50 sine 30 degrees plus minus 9.81 times the time, but the time we're using in this case is this. I'm not going to write this entire thing over here. I'm just going to put a t. It's this. So what we have in this case is 50 sine 30 degrees minus 9.81. Now I'm writing that. 100 sine 30 degrees all over 9.81. And what we do, we cancel this and this. And what are we left with? We're left with 50 sine 30 degrees minus 100 sine 30 degrees. And what we get our answer as minus 50 sine 30 degrees. So this is our final vertical component of the velocity. You can go ahead and punch this on the calculator if you will, but the reason I'm not punching this or this on the calculator is so that I try to maintain the accuracy as possible up to this final point. So this is our final vertical component of the velocity. So let's write it over here too. Let's call it Vy. What is it? It's minus 50 sine 30 degrees. Now I know, now looks like a mess, sorry about that. But this is minus 50 sine 30 degrees. I've labeled it as Vy so that we're reminded that this is the vertical component of the velocity. But it's which component? It's this component over here. The final vertical component of the velocity here. So I'm going to rub this again, including the equation now. So now we've got this, which is the final vertical component of the velocity. What is the final horizontal component of the velocity? That is simple. Since it's constant throughout, like I mentioned in my previous videos, this is simply 5 cos 30 degrees. So I'm going to write it over here. V, I'm going to write it as Vx. I wrote the final vertical component of the velocity as Vy. I'm going to write this as Vx. So this is simply 50 cos 30 degrees. So this over here, the horizontal component of the velocity, is this. And this over here is this. So taking this part and bringing it over here, if we follow the rules of vector addition, we can form a triangle out of this. So in the end, we get something like this. We get something like this. This being what? Vr, what we're looking for. This being what? The horizontal component of the velocity, Vx. And this being what? The vertical component of the velocity, Vy. This part over here, this part, the angle theta, is equal to the angle over here, theta. Let me label it as theta on this diagram. this part. So we've got this part over here being equal to this part over here. That is, this angle over here is equal to this angle over here. So what we want is the size of this angle and the size of this velocity. That is the magnitude of the final velocity. Let me put this triangle over here now. Let me rub all this and put it over here. So we've got a triangle like this. Vx, Vy, and Vr, and our theta over here. So the first thing we want to find here is the angle. Let's find the angle first. Now we already have Vy and we already have Vx. What we don't have in this case is Vr. So we can utilize those two in order to find theta by bringing into mind our acronym Projectile. So in this case we've got the opposite and the adjacent. Opposite and adjacent. So we're utilizing tan. So we've got tan theta is equals to Vy. What is Vy? Now we only want the magnitude of Vy in this case, so I'm not going to take the negative. So we've got 50 sine 30 degrees all over what? Vx. What is Vx? 50 cos 30 degrees. 50 cos 30 degrees. And if we cancel these out, we find that theta is equal to what? Is equal to arc tan sine 30 degrees over cos 30 degrees. And if you punch this into your calculator, you should get the value 30 degrees. So our theta over here is equal to what? Is equal to 30 degrees. So we're going to record it over here because of space. Hey, sorry guys. 30 degrees. And where is our theta located? Our theta is located at this point or at this point. But since these are z angles, that is this angle and this angle being this angle over here. Since these are z angles, this is also 30 degrees. So we've already found the angle at this point, 30 degrees. So let's rub this off so that we find what now? We want to find Vr. So how do we find Vr? We find Vr by simply utilizing the Pythagoras theorem. So in this case, Vr is simply Vy. What is Vy? Again, I'm taking the magnitude. That is 50 sine 30 degrees. I square this. And Vx, what is Vx? 50 cos 30 degrees. And I square this, and we take the square root. So the Pythagoras theorem in this case is simply Vr squared is equal to Vy squared plus Vx squared. But in this case, I simply made Vr the subject of the formula by taking the roots on both sides. So if you punch this again into your calculator, you should get Vr is equal to 50. So if I'm to put the units now, this is simply 50 meters per second. So Vr over here is 50 meters per second. Vr over here is this. So this, the magnitude of the velocity of impact is 50 meters per second, and the angle over here with the ground is 30 degrees. So it's like what I said in the beginning. we've got 50 meters per second and 30 degrees. Again, for this, the only difference now, I'm not saying these velocities are equal. No, the magnitudes are equal, yes, and the angles are equal, yes, but the velocities are not equal. Why? This is in a different direction, and this is in a different direction. So how do we write the velocity now? How do we write out the velocity? We now found VR as 50 meters per second. Keep this in mind. Or we can write it over here. Let's write this as VR is equal to 50 meters per second. Now, if you were asked to express the velocity in three significant factors, now for the magnitude, that would be 50.0, and for the angle, let's say they want you to express it in one decimal place, this would be 30.0 degrees. So, but that's not what I'm requiring in this case. So we're simply going to use this and this. So the velocity at ground impact is what? Is 50 meters per second, 50 meters per second at an angle of 30 degrees to the ground surface. So this is the velocity at ground impact. So it's 50 meters per second at an angle of 30 degrees to the ground surface. The ground surface being this. So if we were considering this angle over here, it will still be 30 degrees. But in this case, we're considering this angle. So 50 meters per second at an angle of 30 degrees to the ground surface. That is the velocity at ground impact. So notice that we found the raw velocity here, and we also found the what while we were working through the question. We also found the time of flight. So in this case, like I said, the time of flight is simply t1 times 2 or t2 times 2 or t1 plus t2 if you will. So we're able to compute not only the raw velocity, but before we got to this, we also computed the time of flight. You can go and punch this on your calculator so that you find the value if you will. But what we needed most was this. So this is how you calculate the velocity at ground impact. I'm going to be looking at more questions relating to velocity. This is only the first example or the first question we're looking at. But in the future, we're going to be looking at more questions which attack this topic at different angles so that you get a feel of how these calculations are performed. So that is it, guys. Thank you very much. Please leave a like, subscribe, and comment if you enjoyed the video. See you in the next one. Thank you.